So this is high level paper 2. I'll try and make my commentary as clear as possible, but please bear in mind it's Fayyaz and so therefore crazy out there, and there'll probably be the odd invasion from a purring cat. Here we go with question 1. The best thing to do with these kinds of questions that look really strange is to remember that underlying the questions, especially question 1, you will find that there will be some really, really simple physics going on. Part A of every question has got to be straightforward and easy, and then it gets a little bit more complex as you delve into the question. So never be scared by an unfamiliar situation. Okay, so what's going on here? In the drop tower shown, containers with experiments inside them are fired upwards inside a vertical tower. The container moves under the influence of gravity and eventually falls back to the bottom of the tower. Most of the air is removed from the tower so that the air resistance is negligible. While in flight, the container and its contents are in free fall. So it's a bit confusing because it talks about so many objects. So it's important to look at the diagram. What's the drop tower? Well, it's the entire container. And in order to perform experiments, small containers inside that big tower are launched. And then we have a little tank here of styrofoam spheres. So you can imagine this little container being shot up into the air and then landing on these styrofoam spheres and probably sinking to make a hole. Let's have a look at question A. The container is fired vertically upwards with an initial speed of 48 meters per second. Determine the time that the container is in flight. This is a really straightforward equations of motion question. So the first thing that you must always do with an equations of motion question is to write down the symbols for SUVAT, fill the information in, and write the equations down so you can begin to choose which is the right one. So I'll do that now. Okay, so here is the information that we are given. We're told that the initial velocity is 48. We're told that that we need to find the time of travel. Now, I've broken it up into 2 journeys, assuming because there is no air resistance that the container will rise to the top and then come down in a kind of symmetrical type of motion. That means the time that it takes to get to the top will be equal to the time it takes to get to the bottom. And that gives us a little bit more information. It gives us the fact that the final velocity, when it reaches the top, is 0. And it also gives us the acceleration, which as it's moving upwards, is minus 9.81, which is a deceleration. So do we have enough information to find t? Well, we do if we use this equation, v equals u plus at. So let's fill in the numbers for that equation. Okay, so substituting our values, we end up with 0 equals 48 minus 9.81, and that would give us a value for t using 2 significant figures, because that's the minimum significant figures that we're using. So our t would be 4.9 seconds, but of course we'd multiply that by 2 because it rises to the top and then falls down again to give us 9.8 seconds. And if you have a look at the mark scheme, that's clearly laid out for you. So the answer is 9.8 seconds. Please remember significant figures now and units. Now what happens in this part of the question? Well, when the container reaches the top and then falls again, this time it's falling and its velocity just before it hits the styrofoam balls is 48 meters per second. Okay? So I'll put that information there, 48 meters per second. And what happens is, as soon as it gets to the styrofoam balls, there will be a resistance force that will decelerate it. That means it will give it a minus acceleration. So its initial velocity, u, is going to be, rub that off, that's a mess. hang on, let me draw this neatly somewhere else. So here we go. The ball falls as it enters the styrofoam balls here. Its initial velocity is 48 meters per second, and because it's falling into these styrofoam balls, it slows down and it stops, and the final velocity is 0. So why am I telling you this? Well, it says at the end of the flight, the container of total mass 480 kilograms falls into a tank of styrofoam and slows down. The container stops after moving a distance of 8 meters. So calculate the average force that acts on the container. Now we have a lot of like motion information, and we have a mass. So what we're looking at is this relationship, force equals mass times acceleration. If we can find the acceleration, then we can find the force, and we can find the acceleration using the equations of motion. So let's go back to the ritual of writing out SUVAT and finding which equation to use. Okay, so as you can see, we have a displacement of 8 meters, initial velocity of 48, final velocity of 0. And so if we have a look at our equations, it seems that the most appropriate one is this one in order to find our acceleration. So let me fill out that equation for you. Okay, so if we do 48 squared, take it over to this side and divide it by 2 times 8, we end up with minus 144 meters per second squared. Okay, so that's our deceleration. And then the force that acts on a container due to the spheres, well, if we go back to this equation, we have force equals mass, which is 480 kilograms, times acceleration of 140, okay, which gives us an answer of, which gives us 6.9 times 10 to the 4 newtons. Okay, again, be very careful with significant figures at this stage. We should be using the correct number of significant figures. 2 to match the 2 that we have here. And don't forget the units. And now we have a complete change of topic. Same question, but different field of physics. The tower is 100 meters high with an internal diameter of 3.5 meters. When most of the air has been removed, the pressure in the tower is 0.96 pascals. So determine the number of molecules of air in the tower when the temperature is 300. Now this is a simple relationship for PV equals nRT. Because if you can find the number of moles, then you simply multiply the number of moles times Avogadro's constant, which is 6.02 times 10 to the 23. Okay, so that would give you the total number of molecules. So let me fill in the numbers there. Okay, so let's have a look at our values. We have a pressure of 0.96, and careful checking the units as well, because they could have sneaked in a kilopascal there, but they haven't. So it's 0.96. Our volume, well, we don't know what the volume is, but we have to assume that it's a cylindrical shape. Okay, so well done those of you who did that. And of course the volume of a cylinder is the height times the area of this surface here. We're given the diameter, so we would need to do 120, which is the height, times pi times 3.5 divided by 2 squared, okay, because that would give us the radius. Now, interestingly enough, the mark scheme is incorrect, and I've double-checked this with the exam board. Believe it or not, mark schemes can actually be wrong, but here they are. The internal diameter here is 3.5, and in the mark scheme they use this as the radius, but that is a mistake. Okay, and I'll try and mark that on the mark schemes that you're using. Okay, so if we work all of this out, we should end up with a value of n of Calculating all of this out, in the end, we end up with a value of n. Let's put it over here. N equals 0.44. And to find the number of molecules, we now multiply that by Avogadro's constant. So 0.44 times 6.02 times 10 to the 23. That gives us a final answer of, I'll write it down here, 2.65 times 10 to the 23. How many significant figures are we using? Well, we could actually bring it down to 2 because pressure has significant figures of 2. Okay, so the answer would actually be 2.6 times 10 to the 23. In the next question, outline whether the behaviour of the remaining air in the tower approximates to that of an ideal gas. Does it follow this ideal gas law? The answer would be yes. We are dealing with 300 Kelvin, so the temperature is high enough and the pressure is low enough to expect ideal gas conditions. So here we have another motion question. This time it's a velocity time graph question. The container can also be released from rest at the top of a tower. The graph shows how the container velocity varies with time from release with a tower in a partial vacuum. So if we picture this, here's our tower and our container is dropped, and when it hits the styrofoam it slows down. So what we're seeing here is it starts at the top, so the graph begins when the container is dropped from the top there, and its velocity increases uniformly, meaning its gradient is uniform and equal to 9.8, okay, or 9.81, and then as soon as it hits the styrofoam, so this point here equates to that point there, it rapidly slows down. And the quantity that is represented by the shaded area, well, you should remember that the area under a velocity time graph is distance. So it's the distance inside the styrofoam while it slows down. Okay. Now, if air is then released into the tower, you won't have this perfect slope now, okay, because g, the acceleration due to gravity, okay, would not be 9.81. It would be affected by air resistance. The container is released from the top of the tower when the air in the tower is at atmospheric pressure, so it's going to have normal air resistance. Using the axes in E, sketch a graph to show how the container velocity varies with time. Well, what happens to the acceleration when you have something falling and it's prone to air resistance? Well, you have a force due to gravity, which as the velocity of that object starts to increase, what you will have is an upwards force called air resistance, which will balance out that force there. That means that we will have a net force which will start off at a maximum and will slowly decrease as the air resistance builds up and matches it. Now, because of that, because your force is decreasing, your acceleration is also decreasing. And acceleration is the slope of a velocity time graph. So you should find that the velocity time graph slope decreases, and it also takes longer because it's not going to fall at the same time. It's going to take a little bit longer to reach. Could even go so far as to say, right, well, if the velocity just before it touches the styrofoam is lower, it isn't actually going to cover so much distance. Okay, so this part of the graph could be smaller. it also has to be clear that the height of the tower is still the same. So this area here should be still the same as the original area under the graph because it's falling from the same height. Okay, so we're looking for something like this. The gradient decreasing, it going for longer, and the area being more or less the same. Okay, so we're going to use Kirchhoff's law on this question, and Kirchhoff's laws state that first, the current going into a junction, let's take X, will equal the current leaving. So if we consider I1, the current flowing this way, should add to the current flowing this way. Okay, so therefore I3 is equal to I1 plus I2. But that's not the end of it. Kirchhoff's laws are also about EMF. If we consider any loop, we would know that the EMF in a loop, in a fixed loop, so it could be this one, matches the potential difference that leaves. So the energy provided by the 9-volt battery will be given as potential difference here and as potential difference here. Okay, so we can write a few equations there as well. So we can see that if we show these potential differences, V2 being the potential difference across the 3 ohm resistor, V3 across the 2 ohm resistor, and V1 across the 6 ohm resistor. So if we have a look at this, we have, let's look at this loop. The EMF is 9 volts, so 9 volts equals V2 plus V1. Okay, but we need to demonstrate that in terms of current and resistance. V equals IR. So if you substitute those values in, okay, for V2 and V1, we would have 9 equals 6 I1 plus 3 I2. Okay, so that's our second equation. And let's try our third situation here, which is the 12 volts. And what we're looking at now is this loop here, okay? So this EMF would be equal to the voltage V3 plus V1. So I'm going to write that out, the two ways that we did it here. I'm going to do it in terms of V3 and V1, and then express it in terms of I1 in this resistance and I3 in this resistance. Okay, and here you have it. It's 12 equals V3 plus V1, and if we expand it out, it's 12 equals 2I3 plus 6I1. So what have we got? We've got 3 equations. We've got equation 1, equation 2, and this is equation 2, and this is equation 3. So we just have to substitute these into each other until we get I1, this one here. So where do we start? Let's have a look. I1. So we'll make I1 equals I3 minus I2. Okay, so that's good. And now let's have a look at this. Let's see what I3 is equal to. Well, if we use this one to find a value for I3, okay, so we have, using this equation, 12 equals 2I3 plus 6I1. If we make I1 the subject of the equation, if we make I3 the subject of the equation, then I3 will equal 12 minus 6I1 over 2, which simplifies to 6 minus 3I1. Okay, so we will eventually put that in here, but now we're going to do exactly the same with this equation, so we can have an expression for I2. Okay, so as you can see, you have I2 equals 9. Bring that over here. 9 minus 6I1 over 3, which simplifies to 3 minus 2I1. Okay, so we have I3 in terms of I1, and I2 in terms of I1. So now we need to put them into this equation here. This one, oops. This equation here. Okay, so here we go. Last bit. We're almost there. So this was our final equation. I1 equals I3 minus I2. So we take I3 from over here, substitute it in for I3. Okay, so it's this bit. And then we have I2, which is this here, and substitute it in here. Okay, if we expand out the brackets, because this is minus 1, so we end up with 6 minus 3 equals 3, and minus 3I1 minus 2I1 gives 3 minus 1I1. Okay, so we bring that over there. 2I1 equals 3. And finally, our final current through that branch is 3 over 2, 1.5 amps. Okay, seems like a lot. It's a very long procedure, but it's a simple one once you know how to do it. Now this one is relatively easy in comparison. We have calculate the potential difference between X and Y. Here's a reminder, X and Y. You have a 6 ohm resistor and the current going through it is 1.5. So it's 6 times 1.5. Why? Because V equals IR, and that gives us an answer of 9 volts. Outline whether X or Y is at a higher potential. Well, we consider the conventional current. So X is higher because of conventional current. Okay, so we would assume that the current flows from X to Y. So now the photoelectric effect. A student carries out a photoelectric experiment in which radiation is incident on a metal surface in a vacuum. So what's actually going on here? Let's have a look. A photon of energy arrives on the metal surface and enables the electrons to escape. That photon of energy has an amount of energy equal to h, Planck's constant, times the frequency of the incident light. So the energy arriving is equal to hf. As that photon of energy is absorbed, a small amount of it is absorbed by the electron and used to escape the metal that surrounds it. So that energy that it pays to escape is called the work function. So the total amount of energy that the electron has as it leaves the metal is going to be equal to the energy that arrives, hf, minus the work function. Let's tidy that up. Okay, so you can see the full equation here. This was Einstein's equation. Now this energy that it has left over is kinetic, and the electron can move, usually around a circuit. Photon energy minus the work function. Now the question asks, why these photoelectrons are not emitted from the metal unless the frequency of incident light exceeds a minimum value. Well, the first thing you need to say is that the energy that arrives depends on the frequency. So the photon of energy is related to the frequency of the light by E equals hf. So that's the first bit. And then secondly, that hf must exceed the work function in order for the electron to be able to escape. So as long as you've got those two elements in your answer, you've mentioned hf and you've mentioned greater than work function, you'll get full credit. Now these graphs are incredibly common. So a graph of the results of the experiment show how the maximum kinetic energy, Emax, of the emitted photoelectrons varies with the frequency of the incident radiation. So if you increase the frequency of the photon that arrives, how does the kinetic energy increase? Now we need to go back to our Einstein's equation because this is actually a linearization question. So let me write that down. If we look at Einstein's equation more carefully, we can see that it follows a linear path. So if we put kinetic energy on the y-axis, and indeed it is on the y-axis, and the frequency on the x-axis, as you can see that it is, then you can get two very, very important pieces of information from the graph. The first one is that the gradient of the graph will give you Planck's constant, and the intercept will give you the work function. Now this is a common question, and be careful because they do sometimes switch these around, so you might have to change Einstein's equation a little bit for it to fit, but pretty much it's the same idea. So the following questions are how to work out Planck's constant from the gradient, how to work out the threshold frequency. Now we'll do that one first. The threshold frequency, by definition, is the frequency at which the kinetic energy is zero. Now what does that mean? That the electron escapes, but it doesn't have any energy left over. That means that the photon energy arriving just equals the work function. And if we think about that, we look at our graph again, we can see that at that situation, y, because kinetic energy is on the y-axis, equals 0. So where does the line hit where the y-axis is 0? So that would be at this point here. So what you would need to do in that case is follow the line down to where it hits the x-axis, because at x equals this point, y equals 0, and therefore the kinetic energy equals 0, and HF equals the work function. The value of intercept on the f-axis is approximately 9.3, and don't forget to read the axes. Okay, so it's times 10 to the 14 hertz. Okay, which you can see if you follow this line down. In the next question, we need to find Planck's constant. And as you can see from our linearization, Planck's constant will be equal to the gradient. So it's important that you show your read-offs. Okay, so you read the axis carefully and you actually show that you're doing it from the gradient. Some of you tried a few other methods, just substituting some values into the equation. That is not the appropriate way of doing this. You must find the gradient. Okay, so I've done a rough gradient here. So if you see my read-offs on my y-axis, approximately 3.4 minus 1.4 here. You can do this on your paper much more accurately. But this is in evolts, and Planck's constants must be in SI units. So you need to multiply this difference, 3.4 minus 1.4, by 1.6 times 10 to the minus 19 to get the energy in joules. And you divide it by the x-axis difference, which was approximately 1.75 minus 1.25. Okay. Again, answer of about 6.4 times 10 to the minus 34, but anything between 6.2 to 6.7 is considered to be a good range. The work function in evolts for the metal surface, okay, so once again, using linearization, this time we're looking at the y-intercept, because if we have yx minus, plus C. Okay, what we're looking for then is the work function, which is that thing there. So if you go back to your graph, which I can't do on this program, but you can, you now need to find the y-intercept, which if we go back to our graph, okay, if you carry on the graph until it goes down and hits the y-axis, you just read off the work function from the y-axis. And you should get an answer somewhere along the range of, let's see, 3.6 to 3.8 EV. Okay, you can do it that way, or you can multiply out by and giving the answers in joules. The student repeats the experiment with a different metal surface that has a smaller value for the work function. Draw a line to show how Emax varies with the F. So if we look at our graph, basically for the same frequency, we have a look here at the point where the photon energy equals the work function, so there's no kinetic energy left. That would happen for a lower frequency. So our photon size, our HF, will be smaller, so therefore our frequency, our line, is shifted along this way. Okay. And what does it mean if we shift it along here? Not only does our photon size that makes this whole thing happen appear to be much smaller with a lower frequency, you also have a much lower value for the work function. Our intercept with the y-axis is now much lower. What is also very important is that the gradient, however, which is Planck's constant, is still exactly the same. An energy question here, and this is actually a really simple question, unsurprisingly. A power station burns natural gas at a rate of 35 kilograms per second. The power output of the station is 750 megawatts and the efficiency is 38. Calculate the energy provided by the natural gas each second. So basically we have power output, we have the efficiency, and now we just need to find energy each second, which is actually the power which is coming in. So this is a really simple efficiency question. Efficiency equals power out over power in times 100. So if I put those values in, okay, so we have 750, remember it's megawatts, we can add that in at the end, over 0.38, which is simply the percentage, 38 divided by 100, okay, and we end up with a power of 1.97 times 10 to the 9, remembering that this 750 was a megawatt answer. Calculate the specific energy of natural gas. Okay, now the definition of specific energy is very straightforward. It's the amount of energy. Okay, so the definition is the amount of energy per unit. Per unit mass. Going a bit crazy here. The amount of energy per unit mass. So what is the energy that's coming up per second? 1.97 times 10 to the 9. What's the mass? 35 kilograms. So it's 1.97 times 10 to the 9 divided by 35, which gives us 56 megajoules per kilogram. 56 megajoules per kilogram. The rest of the question you can see, read off because they're pretty much just standard theory questions on the mark scheme. I'm going to go straight to the numerical question, which is part D. Okay, so here's a nuclear power station question, and we have our decay equation here. Identify the value of x. Basically, add up all the left and the right sides to find the value of x. We've obviously got a certain number of neutrons, and in order for this to add up, so 235 plus 1 gives us 236 nucleons on this side. And then if you add the other side, if you add the nucleons on the other side, you end up with 233 over here. So there's a difference of 3. So how many neutrons do we have? We must have 3 in order for this to balance. So the answer is 3. Okay. So for the next question, we just need to add up all these masses. Using the equation from here, we substitute these masses in, remembering that we have 3 neutrons. Okay, so we would need to multiply this by 3. Okay, so on the left side we have uranium, 235 plus 1 neutron, so we would add these 2 up. And then on the other side we have these 2 elements, right? So we'd add these 2, as you can see them there, plus 3 neutrons. And then we would find the mass difference in U's. Okay. You should find that you get a mass difference of 0.816 U's. And then we need to convert that into megaevolts. Now remembering that 1 U, we'll put it over here, 1 U equals 931.6 megaevolts. You can easily make that conversion. And you should get a final answer then of 760 megaevolts. Oops, my screen is falling apart. 760 megaevolts. There you go.